All right. Well, as uh, I'm the graduate advisor in mechanical engineering, and what I wanted to do is tell you a little bit about the graduate program and some of the faculty and some of the research that are ongoing at the University of Tulsa. So with this, I will start. Let's see. Yeah. All right. Well, as you may all know, we have three graduate programs in mechanical engineering. One of them is the Master of Engineering in Mechanical Engineering. And that Master of Engineering is there is only coursework. There is no thesis option. And there are some engineers that they would like to have a lot more in depth of a study in mechanical engineering, and these are non-thesis. Normally, we don't support students who are on non-thesis, but they could get some tuition fellowship from graduate school. If they have high scores, normally they get some tuition fellowship from graduate school. We do have a Master of Science in Mechanical Engineering program, and normally that's 24 hours of coursework and 6 hours of thesis. So, and thesis, normally you get involved with faculty members and they have to approve your thesis. So you have to get in touch with a faculty member in mechanical engineering to be able to study the Master of Science. And of course, a PhD program in mechanical engineering, normally you have to have 72 hours, and that's beyond the BS degree. And this means that if you have taken already 30 hours for your master's program, all of those hours will transfer to the PhD program. And that includes both coursework and research. So both of your coursework and thesis hours will transfer and will be counted in these 72 hours. So, there is a lot of details here that I'm going to omit, but normally right now we are in a process of changing some of these. So we are normally reducing some of these, but for now it's 42 hours of coursework, and that includes independent study. And then we also have 24 hours toward your research and dissertation. That includes your 6 hours of MS thesis. And then for dissertation, you have to have a proposal for dissertation that you prepare with a faculty member in mechanical engineering, and then you work on your dissertation normally after you're done with all of your coursework. Regarding some of the available scholarships, uh, we do have a WUBank, Wilford WUBank assistantship, and this is competitive among the applicants, and it's only for U.S. citizens, uh, this assistantship. We do have some teaching assistantships that are offered mostly to PhD students, and teaching assistantships are meant to help graduate students, provide them with some funding and also some research, to for their coursework. And normally they get a stipend as well. And they have a duty to help faculty members and they also sometimes they help in the labs. So those are the teaching assistantship duties. And then research assistantships are offered by faculty. Faculty who are conducting research, they offer research assistantship. And those are limited because, they're based on each faculty member has a number of assistantships. And then for right now, we do have some uh, dissertation completion fellowships. And normally these fellowships are for PhD candidates during their final years. And again, this one is also competitive too. So you have to be in a good standing and with maybe high scores for your coursework. And it's also recommended that you take GRE, which will be looked at when you're applying for these fellowships. So later, I will answer questions related to any of these topics, and I'm sure you may have some additional questions. But what I wanted to do is now just talk about some of the faculty in mechanical engineering and some of the research work that they are involved in right now. Currently, we have 10 tenured or tenure track faculty members, and we also have additional 3 contract professors who are mostly teaching courses. And here I will introduce the 10 tenured faculty or tenure track faculty members below here. Dr. Henshaw, he obtained his PhD from University of Delaware. He is currently a department chair, and his area of interest is engineering design, including automotive materials. And also, he is very involved in helping people with disabilities. For example, some of his students, especially undergraduate students, they're involved in research for people who have some disabilities, providing some equipment for them. And also his studies include failure analysis, materials, and so on. Dr. Surur Karimi, she obtained her PhD from University of Tulsa. So she, we recruit some of our very good students ourselves. So she's involved in experimental and computational fluid dynamics. She's also involved in erosion of engineering materials, including wind turbines, wind turbine blades. She's developing some experimental facility for wind turbines, and which is pretty interesting. And also, she's involved in erosion of materials for high temperature application, which has some application for solar energy. Dr. Keller, Michael Keller, he obtained his PhD from University of Illinois, and he's currently associate dean for research. He has a few NSF awards. He's involved in multifunctional materials, characterization of materials with autonomic functionality. So he has a website, so you could look at his some of the research that he's working on. Dr. Will Lepage, he obtained his PhD from University of Michigan. He's in material science group, fatigue of materials, finite element studies, and then also atomic layer deposition. He has prepared a short presentation that I'm going to show you guys, show you all after this. Dr. Brenton McClory, he's also a graduate from University of Tulsa. In the past, he worked on erosion also, gas solid flows, liquid solid flows, and also computational fluid dynamics. If I have a chance, I'll talk about computational fluid dynamics a little bit for you guys. Dr. Mohan, he's a graduate from University of Kentucky. He's a co-director of Tulsa University separation technology. They're looking at multi-phase separation. He's also involved in control systems, instrumentation, high pressure, fluid applications, oil water dispersion, system optimization, and also in manufacturing. So he has a broad research fellowship. Dr. Schultz also has prepared a short presentation that I will discuss and show you guys. He's a graduate from Georgia Institute of Technology, and his research is very interesting about biologically inspired robotics, and also about actuation and sensing, system dynamics and controls. Also, he's looking at anthropomorphic hands and grasping, so, which is pretty interesting. And this is me. I'm a NACE and ASME fellow. I graduated from University of New Mexico, and currently I'm a director of the Erosion Corrosion Research Center and also Tulsa University's sand management projects. My area of studies are computational fluid dynamics, turbulent flow modeling, and multi-phase flow, gas, liquid, and solids, erosion, corrosion. I have interest in measurements using laser Doppler velocimeter and particle image velocimeter, which are used for measuring particle velocities. I'll talk about some of my research as well later. And then also we have Dr. Soram. He's a graduate from University of Kansas. He's just retired from being a dean in the College of Engineering and Natural Sciences. And the last and not the least is Dr. Tipton. He is a graduate from Stanford University. He's interested in fatigue of materials, engineering design, materials, and materials processing. And also he has a research project in coil tubing mechanics. So I'm going to just, right now, I'm going to focus and tell you about some of the research projects that are ongoing at University of Tulsa. As I mentioned, one of them is the Erosion Corrosion Research Center, and I will discuss this if I have time after talking about some other ones. Also, I'm involved in Tulsa University sand management projects and Tulsa University separation technology projects. They look at separating oil and gas. And as I mentioned, coil tubing mechanics research projects. And also, I mentioned a few projects in development and characterization of materials with autonomic functionality. For example, materials that can heal themselves if there's a fracture. So that's especially in composites. That's a very interesting research project. And also we have an advanced materials design group and also soft robotics and rehab robotics. So with this brief introduction, I'm going to show you, first of all, I'm going to see if there are some questions that I could address quickly, and then at the end, there will be more room for discussion. So let me end this presentation right now, or let's see. All right, I assume you could still see my screen. Are there some questions that I could address right now about faculty and before I move on? All right, well, if not, I'm going to uh, show you a couple of presentations. One of them by Dr. Lepage. So let me make sure you guys could hear this. This presentation was made by Dr. Lepage. He's an assistant professor in mechanical engineering. And can you see my screen okay, everyone?
You're good.
All right.
Hello, everyone. My name is Will LePage. I'm an assistant professor in mechanical engineering at the University of Tulsa, and I lead the Advanced Materials Design Group. Here's an overview of just 4 of the projects that we have going on. And we are always looking to add new projects, of course, and not all of these projects will be continuing for many years, but some maybe. So this is just a snippet of what we have going on at this point. So I'm just going to go clockwise from the top right. So our first project on the top right is a large collaboration with key cybersecurity experts, including people in our cyber department as well as computer science. And our role is making 3D printing more secure. So it's sponsored by the Army Engineering Research and Development Center, or ERDIC. And our goal is to be the first to publish mechanical properties on a new desktop metal titanium chip. The further goals beyond that, but that's our immediate first goal. We're developing the groundwork for smart systems to secure 3D printing, and on the way, we'll understand the durability of these latest 3D printing alloys. Moving to the second quadrant, top left, we have a project with the Office of Naval Research that's all about making 3D printed metals last longer. So the goal of this project is pioneering a new class of surface treatments for metals with complex shapes. So that could primarily be 3D printed metals, but it's not strictly limited to those. It's really more of a broader class of surface treatment, but to our knowledge, we're the first to do it. It's the process we've developed and invented here at Tulsa, even filed provisional patent on it. But it's collaboration with Purdue University. We're leading the charge here at Tulsa, but Purdue is contributing as well. That's led by Michael Sanded there. And we're inventing a new surface treatment approach. It's flash melt the surface of metals. It uses the same physics as rock salt for melting ice on the road in winter, for the eutectic reaction. So it's a fun project. We're 2 years in, more years ago. Moving to the third quadrant in the bottom left, we have a project that is in collaboration with folks at the University of Michigan. Gerard Gordon is the PI. Linda Tan is a co-PI. In my group, we're also co-PIs on it. It's designing 3D printed rocket nozzles, really alloys for 3D printed rocket nozzles. We want to be the first to give foundational understanding of copper, niobium, titanium for 3D printing. It's a specific kind of 3D printing called directed energy deposition. New process route could be promising for rocket engines. Copper is there for conductivity, titanium is there for lightweight strength, and then the niobium is an inner layer between the two, kind of a glue alloy process. So this project just started this year, and we've got 3 more to go. And then finally, moving to quadrant 4 on the bottom right, We have a project that is zooming on the fatigue of shape memory alloys, the memory metal. We want to get a clear understanding of the mechanism of crack initiation as defects, things like inclusions or scratches on these materials. Doing cutting edge experiments, we can zoom in a micro scale with scanning electron microscopy and then map strains and pinpoint damage there at the micro scale. So it's a relatively uncommon technique, relatively unique capability we have. We take that data and we combine it with statistics and artificial intelligence to understand what kinds of defects cause failure. There could be an unlimited possibilities of what these defects could look like. We want to know which ones are really problematic and which ones are not. So that's just a snapshot of what's going on in our group right now. If you have any questions, just send me an email. We'd love to talk and just tell me what you're interested in and why specifically our group might be a fit. And hopefully see you on campus. Thanks.
Okay, very good. Well, let me see if I could share with you another presentation from another faculty member. So I have to figure out how to do this. Okay. Can you see my screen? No? Soft robotics?
Yes, we can see your screen.
Very good, very good. All right, let me play this then.
My name is Joshua Schultz, and I'm the director of the Biological Robotics at Tulsa, or BROT Research Group. Today I'm going to introduce you to some of the key concepts and major challenges in soft robotics. When robots are made of soft materials that deform significantly under load. I will also introduce you to some of the efforts the members of the BROT group and collaborators are performing to meet those challenges so that soft robots can do useful tasks in the physical world. Traditional robots have done a good job of automating manual processes in factories where everything the robot must handle is fixtured in place or has its coordinates provided by machine vision. But how effectively can a traditional robot operate in an environment like this? Notice that not only in the red circles, but also under the neoprene sleeve are traditional robotic revolute joints. Eventually, when the environment becomes too cluttered, the robot runs out of joints and can't bend enough to navigate the environment. The BRAT group flips the traditional paradigm in robotics. Instead of trying to improve the precision and planning of robots, we try to make robots that are less precise and give the environment a say in where the robot goes. This notion, combined with high amounts of embodied intelligence within the robot and the ability to make decisions autonomously, will help robots succeed at new tasks in more uncertain environments. Another way that soft robots flip the paradigm is that they are molded from soft elastomeric materials. Fabricating one is not labor intensive and they are comparatively inexpensive, so we don't expect them to have a long operational life. Nor do we need every single one we make to function well. We can always try again. Our soft robot, which we affectionately call Squishy, moves by inflating a silicone elastomer chamber with compressed air. One side is reinforced with fabric and effectively has zero strain, while the other side is unreinforced and can stretch readily. So by inflating, it will reach as it bends. This, of course, will only make a single path in free space. Not much of a working volume, but we're exploring ways to selectively stiffen different patches of the unreinforced elastomer. This will deform the inflation displacement curve, resulting in a larger volume the robot can reach. So how do you know where your robot will go and where it is in space? For traditional robots, we can measure the angle between each link using an optical encoder, and this is no more than a complicated trigonometry problem. But for soft robots that can stretch and bend anywhere along its length, this can be quite difficult for two reasons. First, unlike traditional robots, which can only bend at specific locations, a soft robot can bend anywhere and everywhere along its length, posing an instrumentation challenge. Second, even if we did have some sensors that return a signal, we don't have a way to represent and reconstruct where the robot is from those signals. The BROT group is confronting these challenges from a variety of avenues. Most existing methods to represent the robot configuration and encoding that can be used to capture where the robot is in space Assume the robot is a long, slender rod with continuous curvature, like what you see in the upper left. But as you can see in the other pictures, for robots like Squishy, this is not the case at all. Brought member Garrett Williamson is using urethane fibers embedded in the chamber wall to carry light within the wall chamber at various locations. When one of them is kinked by a wrinkle, light is lost, and the signal can be used to detect that the wrinkle has occurred. As you can see in the plots, the results follow what we get from an expensive motion capture system rather well. The Brock group is also exploring additives to the light transmitting fibers so that they can have the same elastic properties as the chamber walls and integrate into the soft robot seamlessly during the molding process. Brock member Peter Bowie took a different approach. Instead of using fibers within the chamber wall, he illuminated the hollow bore of the robot with light, with 4 light sensors at the other end. When the robot bends, the amount of light incident on each sensor changes. He combined this with information about the orientation of the tip using an inertial measurement unit and applied this using machine learning. None of these sensors cost very much, and they are easy to integrate into the soft robot. Recall that one of the major benefits of soft robots is that if they encounter something in the environment, they naturally bend to move out of the way. Using this method, once the robot has been trained by pushing in different directions, the learn model will tell you where on the robot surface it is being pushed and from what direction. Now that we have sensors to measure signals as the robot moves, we need some way to encode a set of variables so that we can derive a set of ordinary differential equations to describe the movement of the robot. This way we can study and eventually control it. The Brock group and collaborators have developed a method where we discretize the soft robot into a series of disks connected by inextensible threads. If you thought the thread had something to do with the fabric reinforcement, you're right. The thread can't stretch, and so it constrains the movement of the disk so that the disks follow the path of the chamber as it moves throughout space. This gives us 5 variables per disk to represent the motion of the robot. If we need more accuracy, we can just discretize the robot more finely, i.e. more disks, but this means more variables and more ODEs. Using the disk thread model, we can easily animate the motion of the disks and study the way the soft robot will move. But by now you may be thinking, all these mathematical models seem interesting, but do they really predict the type of behavior that you will see in a real robot? Well, we've learned that Squishy has a few tricks up his sleeve, and there are a lot of properties of this fabric reinforced composite that we don't understand very well yet. Peter Bowie led a team of undergraduate researchers to investigate this. They built a lot of robots. And with a major assist from doctoral student Caroline Schell, they learned that soft robots' motion varies considerably from robot to robot, even out of the same manufacturing process. Their behavior changes as the materials age, and their motion exhibits hysteresis effects. They follow different paths, bending out and back, and this intensifies the faster the robot moves. This means that any characterization you make of the robot to figure out where it is in space will expire almost immediately. And you'll notice that robot number 4 didn't survive that long either. Because of this, we will desperately need those sensing and estimation strategies I spoke about early in the presentation. Peter Bowie is working on developing control strategies that take the hysteresis into account to make sure the robot goes to its intended target.
Very good, very good. Let me see if I could. Can you see my screen still?
Yes, we can still see your
Very
screen.
good. All right, I'm going to tell you a little bit about my research, and you guys have to stop me at say 11:50, so we can answer some questions too. You know, I can go on forever. So I'm going to tell a little bit about Erosion Corrosion Research Center, and basically one of the very major projects in this research work is to be able to develop methods for measuring and prediction of erosion and corrosion for the oil and gas industry applications. We have a joint industry projects that our oil and gas and service companies become a member. For example, each year they pay us some amount for the membership. And what we do is we develop models for predicting erosion and also erosion corrosion. And this project is very important because it has to do with the integrity of the piping and system, and also optimizing production, oil and gas production. So let me just give you a brief example. For example, on this graph, on the vertical axis, I have the liquid rate in barrels per day. This is barrels of oil or petroleum fluid. And on the horizontal axis, I have the gas rate. And this is in millions of standard cubic feet per day of gas. So a point here represent a production rate of oil and gas. And what we can do is develop a method. We have developed a method that tells people if you are on this side, for example, if your gas rate is very high, then your erosion is very high. Could be erosion is removing materials from your pipe. So that's what we predict is removal of materials from the piping system. So we can develop tools like this that can predict based on the flow conditions and also your pipe size, elbow size. We can predict how much erosion is taking place, how much material is removed. And in order to do that, we develop models. We have to conduct experiments, and also we use computational fluid dynamics a lot. We have larger scale flow loops, North Campus, University of Tulsa. We have larger scale loops, and we have 2-inch, 3-inch, and even 4-inch test section. These are just some examples. And this test section can be horizontal or it could be vertical because the direction, gravity is important. So this is just a photograph of this flow loop. And then what we do is we install elbows up here like this. And as the particles and fluid, they go around the elbows, some of the particles are impacting the elbows and they cause erosion. And we measure this very high sensitive equipment. We measure the amount of material loss. And sometimes we also have visible section, view section, that we could view the flow and also some of the particles that are impacting the pipe wall. So here, for example, this graph here that you see the color contour shows the amount of material that is removed, high versus low. You know, as the particles are going up and they want to turn, some of them are impacting the pipe wall and they cause erosion. And erosion patterns are sometimes very interesting, you know, things that are, you know, if they're horizontal versus vertical, they can cause different erosion patterns. And we run computational fluid dynamics. Here I wanted to show you some, if I can run this. Here we are simulating liquid and gas. The gas is red and the liquid is covering the walls. So this is what we call annular flow. And here you could see a simulation of the liquid film on the walls as it approaches the elbow. So some of my students, they ran computational fluid dynamics to show us which part of the elbow is covered by liquid, which provides a cushion or particles that are impacting. So we use CFD, computational fluid dynamics, to predict how the particles they move in a pipe flow. And here, some slugging, when you have liquid and gas in a pipe. So you could see what happens. The liquid is blue and the gas is, gray. So you could see how the liquid slugs moves in it. So my students, they use flow visualization like this to visualize how the flow gas and liquid. Liquid is blue and the gas is, of course, colorless. So you could see how we can visualize the flow and then observe the erosion pattern. Here they paint the walls and they can observe what is the erosion pattern. So we do a lot of studies like that to measure erosion and also observe and understand how this erosion is taking place. So we have different flow loops that students use. This is another flow loop that we have. It's a liquid dominated flow loop. And again, we can measure erosion. And this is a measurement of erosion. And this is a computational simulation of erosion. So, there's a lot of work being done at different, measuring here particles are impacting this surface, and you could see the material that is being removed, so we can predict these, and for different type of flow conditions. These are some animations that my students have prepared for different. So these are showing the particle velocities. So different types of experiments that we use. So we do measure erosion with a smaller scale flow loops and also a larger scale flow loops that I showed you. Also, we have a particle image velocimeter that we can measure the particle velocities as they come off in a nozzle or when they're in an elbow, how the particles are moving. So we are interested in measuring the particle impact speed, because the material removal is depending on the particle impact speed. So anyway, I can go on with this presentation and bore you with lots of work that we are doing at Erosion Corrosion Research Center. But I wanted to see, I know some of you have already applied to University of Tulsa. Some of you are already admitted and waiting to get your visa if you're international students. So I wanted to go around the room if Bree and Molly, if you guys don't have anything else to share. Are you guys wanting to say anything before I did I stop my sharing? Okay.
No, not for me. This is a perfect segue into questions. If you guys had any questions, you can type it out in the Q&A section. It's at the top of your screen. It should be those you see question marks, question bubbles.
Yeah. Are there any questions from the audience? I know some of you have already applied and have been admitted. So do you guys have any questions to ask me or ask Molly about, as I said at the beginning, some of you were not here, some of you are already have been admitted and you're registering for courses. So Molly could help you with that aspect. Are there any questions?
If anybody has questions about enrollment, please feel free to answer. But as I said earlier, I know some of you were not in this session at the time when it started, but for international students who are enrolling in classes, You will be officially enrolled once you arrive on campus and check in with the Center for Global Engagement. But we suggest you speak with your faculty advisor. So for mechanical engineering, that's Dr. Shirazi. Make sure that you have your classes ready to go. You know what you will be enrolled in, and then we can get you enrolled once you come. It should not take very long, and there will be open spots in classes, so do not worry.
Okay, any questions? Don't be shy. I know some of you have been in contact with me. Abby, you had your hands up before. Was it just by accident? Abby?
I think there's one in the Q&A.
Okay.
What types of fields would someone be able to work in with a mechanical engineering degree?
I know some of these students, like Irani, he's coming here, and he has a fellowship, a graduate fellowship, a 3-year program. Some of you have been admitted in a graduate fellowship that this year we have been offering. And this graduate fellowship covers 3 years of your PhD studies. It pays for your tuition and also a stipend. And I know some of the audience here are receiving that scholarship. Nushin, have you applied for your visa yet? Nushin, can you hear me?
Hello, Professor Shirazi. How are you?
Good.
It's my pleasure to meet you and hearing you. Yes. 2 days ago, I received my visa, and I'm so happy to share it with you.
That's very good. Okay, that's good to hear.
Thank you very much.
So have they already put the stamp on your, or they have asked you to send your passport for getting the visa?
Yes. Yesterday I pick up for my visa, but I haven't received my passport yet. I think 2 weeks later I will receive my passport, and that's it. And I have a question also. I would like to know that when is the deadline for the course selection for fall?
Okay, well, I will start answering this, but then I'll let Molly handle that. You know, for graduate courses, normally the classes, they don't get really full. So you normally have a deadline is a week before, courses start. That's definitely, you definitely want to be enrolled in those courses. But some faculty members, they want to make sure they have enough students in a certain course. For example, if we don't have enough attendees in one of the graduate courses, we may not offer that course. So that's the reason for you guys to register for courses as soon as you can. And the process to do that is you normally contact your dissertation advisor. I think in your case, Dr. Karimi and I are your graduate advisor. So you could, for example, send the email to her and I, and then discuss what courses you're interested in taking. So we could do that through email. And then once you once you know what courses you want to take, then Molly can help you to register for your courses. In your case, since you already have a fellowship, then you could even, register for those courses. So is that true, Molly? Is that how they could do it?
Yes, so that's basically the process. You will set up, again, meeting with your faculty advisor to make sure you have those courses listed. Do not worry about classes filling up. We've got spots covered, so everyone will be able to get in the courses that you will need to. But yes, you can apply basically up or register for your courses up until the first day of classes. You can always withdraw from a course without penalty, looking at our academic calendar if needed. So there are things to look at definitely on the website, and I can send that link of the academic calendar so you have a little bit of a better idea of first day of classes, when you can withdraw, when you can still add a class in if you would like to add one in the start of the semester. So I will put that link into the Q&A right now so everyone has access.
Very good, great. All right, Anushin, I hope this answers your question. So we would like you to start, as soon as you can. And also, even if you haven't received your visa or you haven't had an interview for your visa, that may help you. If you have already your courses selected, then you go for your visa application and you could say, well, I have already registered for these classes and so on. So that may help you with receiving a visa because they know that you have been in the process already. So I would recommend as soon as you are admitted and you are applying for your visa or you're planning to come to Tulsa, go ahead and register for courses. So any other questions or Bri, did you have something to say?
Yes, unfortunately, we only have 3 minutes left before Teams kicks us all out. So here's what I'll do. If you guys do end up having questions that were not able to be voiced today, if you have, we'll put our emails into the Q&A section, and you can just send us emails and we'll be able to answer your questions as soon as possible, since we might be kicked off soon. But after you put our information in the QA, then feel free to just send us emails if you have questions or concerns or whatever about your process. But yeah, thank you so much for joining. This was a great turnout. I hope you learned a lot. I will be posting the recording of this on our LinkedIn page. And so I will also give you all the information for our LinkedIn page so that way you have that access as well. But yeah, so this was great. Thank you all so much for coming. Dr. Shirazi, if you had anything else to say.
I could stay a few more minutes. Abby, you had a question? Earlier,
no, I think he was just celebrating.
Okay. I think you are applying right now for the graduate program, so that's great. So I think I saw your application or something. Any question from the audience? You have 1-2 minutes now. So feel free to send me an email if you have a question that I could address, and then related to registering for courses or applying to our program. Barry and Molly could hopefully help you there.
Mm-hmm.
Barry and Molly.
Yeah.
Sorry. Well, thank you all for inviting me, you guys, and also for you guys listening to my presentation.
Yes.
Thank you.
You guys have a fantastic rest of your day or evening, whatever time zone it is. And thank you so much. Bye.
Thank you. Bye, everyone.